the session as per usual. Yep, that looks good. And then I head over to the screen share screen, start broadcast, and a little bit of luck, you should see my screen. Can you see my screen? Beautifully. Now that's how I like it. Excellent. And even running the risk that I repeat myself, please don't forget to register your attendance on Moodle. And Bernardo has already kindly provided the links to the registration. And as we speak, here pops up again the link. Bernardo, you are a superstar. And I think the students really owe you big time. So good man, good man. Yep, that's the right spirit. Well, you didn't say where the zeros should be, Bernardo. In front or behind the decimal? Well, indeed, that is what could happen. And even worse, Edith, there's no unit. Yeah, this is what could happen. Okay, so shall we get started? Because obviously it's Friday and everybody is looking forward to a nice and relaxing weekend. I think you have program level multiple choice next week. I've decided to be really gentle with you guys and do some questions that hopefully everybody will find not too challenging. Okay, so what we have done so far is we have looked at enzymes, and we found that enzymes are incredibly powerful machines. We've done these turnover or KCAT calculations, and we have seen that some of the enzymes that are hanging around in the cell are incredibly fast. They can deal with thousands, 10,000s, 100,000s of substrate molecules every second. And almost every reaction in the cell is driven by enzymes, by these incredibly powerful machines. Of course, this means that we need to really tightly regulate enzymes so that they don't do stupid things or that they, don't even, let's say, endanger life. And that is what this session is all about today. How can we regulate enzymes? How can we make sure that they do what they're supposed to do when they are supposed to do it, and not just simply run totally amok and do weird stuff? So this session is about enzyme regulation. And next week, then, we will start with metabolism. And indeed, we need to give them a sort of a timetable. You, enzyme A, you work only under these conditions, and the other enzyme then has to work under slightly different conditions. So We are looking at enzyme regulation today, and we will expand that then next week, where we look at more global regulation of biochemical pathways. And again, this is then, for example, how products can act as inhibitors. And we will discuss that in more detail, Charlotte, next week when we are talking about general regulation of metabolic pathways, when we really, oops, what was that? That was weird. Is the screen still on? Can you still see it? No. Oh, something weird happened. Okay, let me just quickly go back here. The recording works. Okay, and share screen. That was weird. So hopefully you can see the screen now again. Are we back in business? We are back. Excellent, good. So let us assume for a moment we are just some microbial cells, and we discover a source of food, right? And we want to utilize this food, and for doing so, we have some enzymes, or we would need enzymes. So how do we get these enzymes? How can we utilize the food that we have in front of us if we are a microbial cell, for example? We need enzymes to break down the food, but how do we get these enzymes? Are made by the cells, absolutely. So if we don't have the right enzymes, what we can do is we can do what is called de novo synthesis. De novo synthesis. So what would that involve? Yeah, next day delivery, that raises actually an issue. What does the synthesis of enzymes involve? Well, yeah, we would, first of all, pretty much, yes. First of all, we need to activate the gene for this particular enzyme. We then have to transcribe the gene into RNA. We then have to translate the RNA into a protein. And then we have the enzyme. And that's pretty much, Charlotte, what you just described, right? Now, can you see a problem with that? Gene activation, transcription, translation, probably some processing. Absolutely right. It's quite a time-consuming process. It might take minutes to hours. So time-consuming, and also it costs energy, doesn't it? Making a protein is it consumes a lot of energy. And God knows if we really then get more energy out of the food than we invest by making the protein. And many enzymes are needed, absolutely right, yeah? So it's a little bit sort of, it's not a terribly efficient way. But a lot of cells make use of this mechanism. So they produce the enzymes when they are needed through gene activation. What do we do when we don't need the enzyme anymore? Because de novo just simply means we make them fresh. We make them anew every time we need them. What do we do with the enzymes when we don't need them anymore? We stop producing, yep. But then, do we store them? Well, usually what we do is what we do with anything that we don't need anymore. We just simply put them in the bin, and therefore we degrade them so that we can reutilize the amino acids that we have invested in them. And again, that is a very common process in cells where we have a new situation, we synthesize the enzymes and then degrade the enzymes if we don't use them anymore. And if you think about it, this is a form of regulation. We only have the enzymes present when we need them. When we don't need them, we just, dispose of them. But the downside is it takes long and it requires energy and other enzymes. So maybe we can come up with a more efficient way. And one of the ways that we can deal with enzymes, obviously, we want to make sure that the enzymes only work when we need them. When we don't need them, they don't work. We have already discussed in these lectures is a way how we can sort of modify the activity of an enzyme. So what have we learned? How we can modify the activity, the rate of an enzyme. Yes, we could use inhibitors. You're absolutely right. So if we want an enzyme to be active, or if we want an enzyme not to be active, let's do it like that. Active enzyme, inactive enzyme. We can use an inhibitor that inactivates the enzyme. And we can use lots of different compounds that keep this enzyme inactive. And if it is a reversible inhibitor, then we have also the option of moving back to the active enzyme. Very often, this is either done by the inhibitor no longer binding to the inactive enzyme, or we can have the opposite. So we can have the opposite of an inhibitor. What would you call the opposite of an inhibitor? What would you call the opposite of an inhibitor? Promoter? Activator. I quite like this form of activator. So we usually talk about inhibitors and activators, and instead of, always using this mouthful, make enzyme work again. I like that. Instead of using this mouthful of inhibitor activator, we are generally talking about effectors. An effector is just simply a molecule that does something to an enzyme. So it can be either an activator or it can be an inhibitor, because they have an effect on the enzyme. And we can have a positive effector, positive effector. It has a positive effect on the enzyme, which is another word for activator, or an inhibitor would be a negative effector. So there's a little bit of terminology. When we are talking about these effectors, we are also usually talking about molecules that bind to the enzyme, and these molecules can actually, they are not related to the substrate. Or let me put it this way. Let me start from a different angle. We know that we have effectors. We already heard about a very potent thing, a very potent molecule in an enzyme reaction that can affect the rate. So very potent effector that affects the rate of the enzyme. And every single enzyme that I can think of has this effector. It's a little bit, perhaps a little bit confusing, so stay with me for a moment. What molecule in an enzyme reaction has a massive impact on the rate of the enzyme? What Bingo! Absolutely right. The substrate is an effector. The substrate is an effector. Absolutely right. Because we know in a normal Michaelis-Menten plot, where we plot the rate versus the substrate concentration, we have something like that. So the higher the substrate concentration, the higher the rate. At the moment, forget about the inhibitor. Let's talk about the substrate. Okay? Substrate is an effector. And because the substrate is also the thing that the enzyme changes, substrate is also compound that is changed in the reaction. It's changed by the enzyme. We call this a homotrophic effector. So the substrate has an impact on the activity of the enzyme and is also the compound that is changed, and therefore we call this a homotropic effector. Okay? Are you happy with me? Are you happy with this definition? Does that make sense? So homotropic effector when we talk about an enzyme, when we talk about the substrate of an enzyme. Okay? Now, we also have a very interesting phenomenon sometimes where the substrate, this homotropic effector, has also leads to a very different type of curve that we see here. And in this case, we have almost a situation which is the opposite of what we've discussed on Wednesday, where we have the two substrate reactions. On Wednesday, we had one enzyme that was dealing with two substrates. What I'm talking now is something that is a rather weird effect, where we have one enzyme made up of several identical subunits. Identical subunits. Okay, so one enzyme has several identical subunits and they are catalytically active. What would we call the structure of this enzyme? Is it a primary structure or secondary structure? It is a quaternary structure. So we have, let's say, because I can easily draw this, we have an enzyme. That is our enzyme. And this enzyme is made up of four identical protein chains. So four identical units, and each one of these units is denoted as a subunit. And this forms the quaternary structure of the enzyme. And so we have these four identical protein chains. Now it could happen, and let's say each of these subunits has an active site. Let's say we have an active site here. Okay? So these here are the active sites. So this enzyme actually has four active sites, but they are otherwise absolutely identical. Now, if the enzyme is in this particular state, it has not a very high affinity. So it has a low affinity for the substrate. The substrate does not bind very easily. Or in other words, in this state, where we have these rectangles, enzyme in general is not terribly interested in the substrate, and we need a lots of substrate required. Substrate required. The enzyme is rather sluggish. The enzyme is quite tense. And very often this is actually the natural state when the enzyme doesn't encounter a lot of substrate. The enzyme is sluggish. It's in what is called the tense state. Okay? And I come back to that in a moment. Don't worry. It's in a tense state. Doesn't do a lot. High Km, low affinity. Now, when we add substrate, and when we add quite a lot of substrate, what will happen, what can happen is that, let me take a different color, a substrate molecule binds to the active site here of one of these molecule subunits, so substrate. And as a consequence of binding, we know that whenever we have a binding event, there is quite likely a change in the conformation of the enzyme. So we might end up with an enzyme that looks like this. This is when the substrate now has bound, it changes the conformation of this particular subunit. Okay? Substrate binding changes conformation, changes the shape of this subunit. Changes shape of subunit. And it turns that into this round state. This is very often also called the relaxed state of the enzyme. Now, if you look at my beautiful drawing here, this looks really odd, doesn't it? And it looks sort of uncomfortable. We've got 3 square states and 1 relaxed state. And what very often happens in enzymes that follow a behavior like that is that changing this shape here has an impact on the other shapes. It has an impact in that it changes the other shapes also into this relaxed state. Do you see this? Just the binding of one substrate molecule has an impact on the other shapes. And yes, there is a video on it on the channel. What we find that these round shapes, the round shapes, they are also called the relaxed state. The relaxed state has a much higher affinity for the substrate. So, if we look at the tense state, this has 4 times very low affinity. We bind one substrate just by adding lots of substrate, and we get In the next step, we get a system where we have 4 times high affinity. For the substrate. So we can all of a sudden, by changing the shape, we can all of a sudden bind 4 times the amount of substrate. So we turn it from 4 times very low affinity into 4 times high affinity. And the activity of the enzyme will be much higher then, just by binding one substrate. How would that actually look like in a Michaelis-Menten plot? Absolutely right, Shimmick. This is exactly what happens in hemoglobin, although hemoglobin is not an enzyme. So what we have here, we have our substrate concentration, and don't forget, this is a homotropic effector. Now, we have low substrate concentrations. And a normal Michaelis-Menten enzyme would show something like that. With this particular behavior, let me choose a different color. That's a nice color. We have low substrate concentration. The enzyme does not really bind anything. But once it has bound something, bound the first substrate molecule, it changes its shape into one of these relaxed, and like a sort of an avalanche, the other subunits change and gain affinity and gain speed. And just simply, what happens is the substrate changes the conformation of this subunit, and the other subunits actually see this change. They are forced to adopt this other conformation, this round conformation. And therefore, by just binding one molecule of this homotropic effector of the substrate, we change it into what looks like a sigmoidal or an S-shaped curve. Sigmoidal curve. And that is contrary to this hyperbolic curve that we see for the normal Michaelis-Menten enzyme. And here we have, of course, the rate. Thank you. So in this subunit enzyme, a conformational change is introduced by binding these just one molecule of substrate. And what you see is almost a sort of a switch-like behavior. Switch-like behavior. So low substrate concentration, nothing happens. And then we just need a little bit of substrate concentration to get to the maximum point. And absolutely right. This is hemoglobin is actually the textbook example for this behavior. Although hemoglobin is not an enzyme, it is just a transporter, but enzymes behave exactly the same. And what it does actually is the subunits, if you like, the subunits talk to each other. Talk to each other. So this means as soon as a tense subunit sees a relaxed subunit, it will turn also into a relaxed subunit. This phenomenon sigmoidal refers to the shape of the graph here. Sigmoidal just simply means S-shape graph. So the subunits talk to each other. They cooperate with each other. They sense the different shapes of the neighbors. Do you see what I mean? We have a tense state. The tense state can bind, but not very well. But as soon as the tense state binds, it turns into a relaxed state, into this round state. The neighboring subunits see this change and decide to cooperate and also turn into this relaxed state. This is known as cooperativity of enzymes. Cooperativity of enzymes. Enzyme subunits, I should say. The subunits cooperate with each other. They see a change in shape and say, hey, cool, why don't we do that as well? It's a little bit like GameStop or, Bitcoin or something like that. Just because my mate invested in GameStop, let's do it as well. I don't have a clue why I'm doing it, but let's do it because my mate does it. Because this subunit next door has changed, I will change it as well. And therefore, I can bind substrate much more easily. That is what this sigmoidal shape is. Does that make it clear? Absolutely. I think that's a very good description, Lauren. It's peer pressure, right? It's positive cooperativity. And it leads to a sort of a switch-like behavior. And in this case, the switch is generated by the substrate. The substrate, this homotropic effector, does exactly switches the enzyme on. It's a multi-subunit enzyme, if you like. So this was the homotropic effect of the substrate when we have several subunits. And not every enzyme shows this cooperativity. If the enzyme is just a single subunit enzyme, then it doesn't show this cooperativity. So not every enzyme is made up of these subunits. And if the substrate concentration goes down again, we revert back. So let me draw that here. If the substrate concentration goes down again, we revert back to the original state. Absolutely right. So we basically cycle through it. And the beauty of this switch-like behavior is we only need a little bit of substrate here, a slight change in substrate concentration here to go from basically not on, that's the low state, to the full on, that's the top state. That's one of the models. Absolutely right. So that's positive cooperativity of this enzyme subunits in the right enzymes caused by the homotrophic effector, which is the substrate. You got it? Okay, now, obviously, if there's a homotrophic effector, there's also something that is called a heterotrophic effector. And a heterotrophic effector is basically any kind of effector that is not identical to the substrate. And a positive cooperativity means if one substrate has bound to one subunit, it makes it easier for more substrate to bind to the other subunits. That's, if you like, it's almost like a positive feed-forward loop. Positive cooperativity is a positive feed-forward loop. It's not feedback, it's feed-forward, because it makes things easier for the next one. Okay? Is there something like negative cooperativity? Yes, but it's not very often, and it's basically the same thing as an inhibitor. And homotropic just refers to the substrate. Hetero means it refers to any effector. A heterotrophic effector is any kind of effector that is not identical to the substrate. So that would be your standard inhibitor molecules. Because these molecules are not identical to the substrate. Yes, or they could also be something that looks like a substrate, but is not a substrate. Or it could be, for example, like a small molecule that acts like an uncompetitive inhibitor. So heterotrophic effectors are basically any kind of effectors that change the activity of the enzyme, but are not identical to the substrate. So let's, for example, look at a heterotrophic effector. Here is our enzyme. And here we've got, let's say, an allosteric inhibitor. This would be a heterotrophic effector. Inhibitor, or it could be an activator or something like that, right? But how does it work? Why does it affect the activity of the enzyme when it binds somewhere here? How does it work in this case? What does this effector do? It changes the conformation of the protein. It might change the active site, or it might change the general shape of the enzyme, so that the substrate can no longer bind, or that the substrate can bind easier. It is a conformational change. So these, again, these effectors lead to a conformational change. Well, an inhibitor can't be the same as the substrate, because then it would be the substrate. So there must be a slight difference between the inhibitor and the substrate. And therefore, the inhibitor is not identical to the substrate, and therefore it is a heterotrophic effector. It might have the same shape, but it is not the substrate. It just binds to the active site, but it blocks it. So it's not the substrate. It is a heterotrophic effector. And these heterotrophic effectors lead to a conformational change in the enzyme. So what we can do is, what we can have, for example, is modification of the enzyme. Modifications of the enzyme that lead to conformational changes. We can bind something, or we can attach something to the enzyme. A very common attachment to an enzyme is the attachment of a phosphate group. To an enzyme. We might have coenzymes, although I don't like this expression because it's either a substrate or an effector. I will avoid the expression coenzyme wherever I can. So we might have an active enzyme and we attach a phosphate group, and I draw it like that. We attach a phosphate group Very often, this is caused by another enzyme, which is called a kinase or protein kinase plus ATP. So this protein kinase attaches a phosphate group from ATP to the enzyme, and it turns the active enzyme into an inactive enzyme. Does that make sense? Why does it change the activity? Because we have attached something, like a phosphate group, and that leads to a conformational change. How do we get rid of a phosphate group? How can we do this one here? Going back from the inactive to the active enzyme. Energetically not possible, but it's a nice idea, but that can't happen from the energy, and we will discuss that next week. We dephosphorylate it, absolutely right. And the enzyme that does that would be called a phosphatase. And they just remove the phosphate group. So we have a system of kinase and phosphatase. So we get the enzyme back. Now, this system actually is a very, very interesting system, and I will talk about this system next week because there's far more to it than the eye meets. There is another really interesting system. We can also modify the enzyme, for example, through oxidation or reduction. So imagine our enzyme looks like that, and we've got S here, where the active site is. We have a disulfide bond. Do you think the substrate can easily bind now if we have this state? Can the substrate get into the active site easily, the way I have drawn it? Yes, no? Doesn't look like it, right? However, if we reduce this disulfide bond and turn it into something like that, would that look better for the substrate? That's much easier. Which amino acids actually can form a disulfide bond, BI300? Cysteine. Excellent, well done. So we might have two cysteine residues that block this active site here when they are oxidized and form this disulfide bond. But when we reduce it, they open up in the reduced form and the bond is open. So this might be the active form. This is the inactive form. Actually, lots of enzymes in the upper, the phosphorylate enzyme is the inactive form, that's right. So in this case, with the oxidized and the reduced form is the active form, and the oxidized form is the inactive form. So here, through reduction, we make it active. Through oxidation, we make it inactive. Actually, this is a really interesting mechanism. And if I just have another minute or two, this is an interesting mechanism because plants sense light. Plants know when they have to switch on the enzymes for the Calvin cycle when they produce sugars. How do they do that? They don't have eyes, but what they do is during photosynthesis, they produce ATP and NADPH. This is a reducing agent. This is a reducing compound. So usually the enzymes for the Calvin cycle, for the sugar production, are in the inactive state, in the dark. They are inactive, but when the cell when the plant cell, when the chloroplast produces NADPH, this is converted then into the reduced enzyme, and the reduced enzyme is active. So that's in the light. Now you turn the light off, we don't have reducing compounds like NADPH anymore, and we go back into the inactive form. So you see, we can modify an enzyme with a lot of different mechanisms. We can attach phosphate residues, we can remove them. We can change the environment, reducing or oxidizing. pH is an effector. Some enzymes are active in low pH, and if we change the pH, they become inactive. So we can regulate enzymes very, very nicely. And I think this was sort of the take-home of a message of this. We have, if you didn't get the positive cooperativity, I've put up a video on the BI301 playlist and the enzymology playlist, I think, where I go through that again. And with the phosphorylation and dephosphorylation, we will look into that next week, because again, there is something really, really interesting which baffled scientists for many, many years, because it somehow doesn't look right, but it's incredibly powerful. With that, thank you very much for watching. Have a lovely weekend. Take care, be good, and stay sane. Enjoy.